Okay, yeah. Welcome to lecture unit 5 of the lecture Sampling Methods for Machine Learning. We now had a 1 week break because of a holiday. Now we have to catch up a little bit again, and the next 2 units will also be delayed because of holidays. Yeah, okay, so let's take a look at the overview of the lecture. So we are in the part of non-uniform sampling and in the construction-based part. We consider analysis and synthesis of this construction-based sampling. And we also consider the univariate case and the multivariate case, where the univariate case is always much, much simpler. We will also see today, when we take a look at some sample methods, especially for the transformation-based sampling, that the univariate case is much, much simpler. Okay, we always discuss 2 techniques, the distribution function technique and the change of variables technique. For the change of variables technique, we will focus today on the multivariate analysis. Last time we closed the lecture with the univariate analysis. And then we have to, before we go to the multivariate synthesis, we have to take a look at the univariate synthesis, because this is complicated enough. In the end, we will take a look at generating Gaussian samples by applying the results from the multivariate analysis, with the Box-Muller method. Okay. But my focus today will mostly be on this part, the univariate synthesis. Okay. This is, let me close this here. Okay, so this is what we want to start with. So the multivariate analysis of the change of variable technique. Perhaps you remember what we did last time. Instead of working with the cumulative distribution functions, we focused on using density functions directly. So we just plug in the inverse mapping into the original density function, but then we have to consider kind of a weighting function, a weighting factor, which is the derivative of the inverse function that we use. We will proceed in a similar way here. And here we will focus on monotone mappings directly. We saw a lot of non-monotone stuff, on non-monotonic stuff last time, and you can more or less directly use this also in the multivariate case. So there is no need to focus on that anymore. We can also start with the bivariate case, instead of with the multivariate case directly. Complicated enough. Oh, we have sometimes the. Do you hear that? I don't know why that is. The battery seems to be full. Okay, let's try. I hope it still works. We can start with the bivariate case that is complex enough and contains all the difficulties compared to the 1D case, the univariate case. So what we do is we consider a random variable, a random vector x, consisting of 2 random variables, x1 and x2. And this would be the input, or the source. And then we have a random vector y, comprised of random variable y1 and y2. And then we have this mapping. So we map from x to y, and this is what I always call the transform. So this is the forward mapping. It maps from x, random variable x, to random variable y. But it's interesting, that is the mapping, and please keep that in mind. This is the mapping that we use to map the random variables, and we also use to map realizations of random variables. But when we look at the transformed densities, we always use this inverse mapping, R. So we have a forward mapping, T, But inside of the functions, we always use the inverse mapping, R, yeah, or reverse mapping. That's why I called them transform and reverse transform, so that we can easily recognize which is which. Yeah, and again, the mic is shutting off sometimes. I don't know. So we have this mapping from x to y, component-wise. So we have t1 of x1 and x2 and t2 of x1 and x2, and we do this mapping. And because we focus on the monotonic case, this is invertible. In fact, you could have invertible mappings that are non-monotonic, of course, but we do not look at those. Here we consider or strictly monotonic mapping that we can invert. And this is then the inversion. Here we map from y to x, and this is the reverse mapping, also split up into the component. Can we change something with the mic? Do we have an idea? We can shut it off. No, it's completely full, so the mic should work. Let's give it another try, otherwise I have to take the other mic, but that's a bit more complicated because I have to carry it with one hand, I guess. So we have the forward transform, we have the backward transform, and if these were linear transformations, they would be easy to analyze, but we have nonlinear transformations. So what we want to look at are differential mappings. So locally linear mappings for the analysis. And we saw that for the univariate case already, that we need differential mappings. And this would be dy depending on dx. So I just take the derivative dy1 with respect to dx1, dy2 with respect to dx1, dx2, and so forth. And this gives me then, when you look back at the mapping here, I can do that component-wise. And the convention is for the Jacobian to just consider the first mapping first in the first row, and then the second mapping in the second row. There are also other conventions, but this is the most popular one. And then what we get is this Jacobian, with respect, or we call it JT because with respect to x, dt1 with respect to x1, t1 with respect to x2, and so forth. And this gives us the differential mapping from dx to dy. We can do the same, and we will use this also for the reverse mapping. Now what we do is we use the reverse function here and take the derivative with respect to y1 and y2. So please take a note of the difference. Here we use x1 and x2. Here we use y1 and y2, exactly of the reverse mapping. Why is that useful? In many cases, and we will see some cases today, the derivatives could be much simpler in one of the domains than in the other one. So for example, this derivative could be much, much simpler than that one. So why not just take this one if that is possible? And we will see a motivation why this is useful in a second. So here we have the differential mapping from dy to dx, and we call this Jacobian GR. With respect to the reverse mapping. Why are the Jacobians so important? I have to warn you, I cannot do all the details with this derivation. That would be, I considered that, but that would take at least 45 minutes. So I have a very compressed derivation here, lacking important details. If you're interested in those, we can either do them later or you can just look them up on your own. So the idea is, so this is the scalar case that we did last time. So when we want to calculate Fy of y, then we usually integrate over the wrong domain, the domain of, when we plug in the original domain S into the reverse mapping, so we have R of S, and then we integrate over f of x dx, so the x density. But what we want to have is, we want to integrate of the original domain for y, and then we have to do this change of variables. Perhaps you remember that, We just do a substitution, We substitute x is equal of r of y, and then we take the derivative. Dx is the derivative of r, so r prime of y dy, and then we plug it in, and then we distinguish between the positive and the negative case, so positive slope or negative slope, for monotonous mapping. So that was the scalar case. For the scalar case, the derivation is about 5 minutes. And we did this last time. We can now do a similar derivation for the multivariate case, or in that case, the bivariate case. So this is exactly that, this part, where we still want to change the integration area. And for doing that, we do a substitution very similar to that one, but here we now have the determinant of the JR Jacobian. So the Jacobian of the reverse mapping, similar to here for the one-dimensional case. Why is that so complicated? Because if you have locally linear transformations, so the Jacobians comprise this locally linear mapping. So you can imagine you have an orthogonal system in X, and then you map to Y. And then orthogonality is usually lost. And then you have to calculate, similar as we did here, to kind of relate the areas under the densities. Perhaps you remember this plot, where we have the area in one part of fx of x and in one part of fy of y. Same thing here. And this accounts for the relations of the areas. But we have to calculate in a high dimensional space the area of this parallelogram usually in a high dimensional or in a two-dimensional space. And that's a bit complicated, especially when you go to dimensions beyond 3. In dimension 2, you can use the cross product for that. That is not available then in high dimensional spaces, but still it would take some time, and to do it correctly is really lots of writing, at least. So just believe me, that is correct and is directly related to what we did last time. And then, because this is the integral over Sy, the domain Sy, it's this set, in the original domain, also over fx of x, fy of y1 and y2, then I can do a comparison, and I find out that fy of y is fx of r of y times the absolute value of the determinant of jr. Similar as in the 1D case. So this is our result. Okay. And now we can make good use of that. And with some tricks, we can also get these dual formulations. We had this dual formulation in the 1D case, where I can take the derivative of the reverse mapping or the derivative, or 1 over the derivative of the forward mapping. Same thing here. I can just rewrite this. I can rewrite dx over dy times dy over dx is obviously equal to I, the unity matrix, identity matrix. So this is equivalent to J with respect to the reverse mapping times J with respect to the forward mapping is also identity matrix. From here, I see that JR is equal to JT to the minus 1. yeah, or from here to here. I can also invert that part and also see that this is true. Yeah, so the Jacobians are inverses of each other, which is nice, yeah, which is interesting. Yeah. So for the substitution, same as in the one-dimensional case, I only have to decide for one type of substitution. The other one I get for free. I do not have to do explicitly with this formula. Yeah? I could also use another substitution here. Instead of replacing x is equal to r of y, I can also use y is equal to t of x into the substitution. Yeah? But I can save a lot of work by just using this. Yeah. Okay, so the Jacobians are inverses, but then for the determinants, we can also see quite quickly that the determinant of a product of two matrices, A and B, is equal to the determinant of A times the determinant of B. Yeah? And then I know that the determinant of JR times the determinant of JT is the determinant of JR times the determinant of JT, but we know that this is equal to 1, yeah, because that was the identity matrix, this product. And then we know that the determinant of JR is also 1 over the determinant of JT, which is important, yeah, because then we can directly derive the dual which is given here. That would be the dual formulation. So instead of, perhaps we can take a look at it again. So instead of using this formulation, where we plug in the reverse mapping into the original density times the determinant of JR, let's forget for a second the absolute value. The absolute value is in the upsloping case, we can just ignore it. Yeah, so we have plugged in r of y into fx and then times the determinant of JR. And the dual case, by exploiting this fact, would just be we plug in into fx either r of y or t to the minus 1 of y to make it more symmetric. Yeah, 1 over the determinant of J. Yeah, okay, I think I will now switch microphones.
Ich habe auch wieder den Bändel bestellt, also man kann das schon auch so umhängen. Und diesen Knoten da so reinhängen. Oder war das, weil das an war?
Dürfen die nicht beide an sein? Was ist das? Okay. Can you hear me? So, okay. Yeah. Then let's continue with this microphone. Then we can use this alternative representation. Yeah. So we plug in t to the minus 1 of y into fx, the original, the source density, and then we multiply by 1 over the determinant of jt. Yeah, so exactly as in the 1D case, yeah, we now have these two formulations. Yeah, is that loud enough? Okay. Yeah. Yeah. Try my best so that you can hear me. Yeah. And then we can now go to the general multivariate case, yeah, when we have two random variables, x and y, and they are both from R to the n, yeah, so n-dimensional real space. We again have this forward mapping t, and we have the reverse mapping t to the minus 1 of y, or R of y, as we called it, and then we get exactly the same thing, but for higher number of variables. So the first formulation is again plugged in the reverse mapping times the determinant of JR, and JR is the Jacobian with respect to the reverse mapping. So first row is R1, and then we take the derivative with respect to y1, y2, and yn, and so forth. And one column is related to the first variable, or one variable, the first one, the second one, and so forth. And then we have the dual formulation that I can write down as follows, as fx of x times 1 over the determinant of jt of x. But we know that x is related to y via the reverse mapping, so I can just plug this in and I get this dual formulation, which is a bit more complicated, but as I said, it might make sense to use it when the derivatives are a bit simpler, in that when you use the forward transformation. So this is then the forward transformation, t. Again, the first row is the first entry of t. The last row is the last entry of t. The first column is the first variable, and so forth. This is the standard convention of the Jacobian. And as I said in the beginning, the non-monotonic case can be treated analogous to the univariate derivation. So we then just have a sum over the roots. We have to take care of the sign via the absolute value, and then we sum up the roots, and we can have a changing number of roots, as we discussed last time. So the number of roots depends on where you are in your domain. So that's why non-monotonic mappings are not so nice to handle. But we had a way, we discussed a way how to handle it, but it's a bit more complicated. So do we have questions so far? Yeah.
Are there any specific transformations that are kind of right-handed so that we don't get the absolute value?
Oh yeah.
Beforehand we know before.
We have to make sure that the determinant is positive. We can do that via increasing monotonic mappings. In that case, the Jacobian, the determinant of the Jacobian is positive.
And do we have like more relaxed regularity conditions? So like without saying monotonous, still the determinant is like positive?
Oh, we have to be careful. If it is not monotonic, we cannot use this simple formula, because then we have to take the formula for the non-monotonic case that I just mentioned. Then we have the sum over the roots. That makes it much more complicated. So that is not easy to relax. In fact, in many cases, we have even harder conditions. We will discuss that probably next time, or perhaps a little bit later than that, where we, for example, want to have orthogonal mappings. So that the columns of JT are, for example, orthogonal, stuff like that. So there will be perhaps harder constraints. So we cannot relax the monotonicity, unfortunately. So invertibility is not enough usually. Okay, then. We will go to the synthesis. Okay, and synthesis for the univariate case first. And that is still complicated enough. At least complicated enough to explain. I think once you get it, it's not that complicated anymore, but to convey the idea. So what is our goal? So our goal is to approximate a density y tilde by transforming a simple density to it. So what we learned in the analysis is when you are given a density and you are given a mapping, how can you calculate the result, the fy? Now we consider the reverse problem. So we are given an output density, let's call this target. This is the one that we want to achieve. And we are given a simple density, let's call that source density, and we want to map samples from here to here. That could be one application. This lecture is concerned with sampling. So usually we would draw samples from fx and obtain samples from fy, because this is the density where we don't get samples from. or not enough. Yeah? Could also be one option. We have some samples from Fy, then we want to find a mapping from Fx to Fy to get more samples. That is, in fact, one typical application. Yeah? Then perhaps we just want to evaluate Fy, yeah, but this is complicated to evaluate because we only have samples, or it's just such a complicated density. Then we also want to perform this mapping because with this formulation that I showed you, I can find an analytic expression. It's implicit, but still, because we have this mapping inside, but still I can do an evaluation of the density. Yeah? And as I said, drawing samples is one important aspect of it. Yeah, so what are we typically given? We are given the desired density Fy, but it is important in what form. Are we either given it by just some samples, yeah, random samples? Are we given it by values of the density, which is a totally different representation? So we would have just values of the densities at some point. Yeah, and we could have it in an analytic form, but for example, without normalization constant. That could also be possible. You know? Imagine you have a density, let's say a Gaussian density, and instead of having this squared exponent, you would plug in a polynomial. I will show you a similar example later on. Then you would have difficulties calculating the normalization constant, because the density should be normalized, should integrate to 1, but it's usually very difficult to find the normalization constant. So here we will see a technique where you don't need that. Yeah? So this is very flexible. Yeah? So the synthesis we look at will be very flexible, so you don't even need this normalization constant. Then we select, so this is our selection, yeah? We select some convenient, some simple density, Fx of x. Usually that will be uniform or Gaussian, but there's no need. Could be any density, at least as it fulfills your constraints, your conditions. Yeah, for example, it is easy to sample from, or it has a very simple analytic form. So the uniform density has the advantage. It is constant everywhere, very simple to evaluate, stuff like that. Yeah. Then what we desire is a mapping, yeah, this mapping T, that transforms the simple density to the given density. Yeah. So that is what we want. So in contrast to what we did before, where we are given this mapping, we now want to calculate that. So what we need for that? We need a hypothetical density over y that results from an arbitrary monotone mapping. Fortunately, the monotone mappings in 1D, in the univariate case, are not so difficult to characterize. Yeah? That is totally different in the multivariate case. But here, they are kind of easy to parameterize. Yeah, so we need this hypothetical density, and for that, we just use the transformation, yeah, a parameterized transformation of fx. And we use this dual formulation that we just saw. Yeah, so fx, we plug in r of y. We don't know r of y yet, yeah, because this is the reverse of the unknown transformation and the derivative of r of y. Of course, the parameterization of your mapping that you use should be easy to invert. In the one-dimensional case, not so difficult, but you should also be able to take the derivative. Yeah? So we would like to have kind of a continuous mapping that is invertible, monotonic, or strictly monotonic, would even be better. Yeah, stuff like that. Yeah? And then we want this, yeah, or this, yeah, fy of y, this, this density that results from the transformation should be as close as possible to the given f tilde, fy tilde. Yeah? And there are many ways to do that. Usually we should use a distance measure between the two densities. Yeah? and a distance measure that is made for comparing densities, not just some distance measure, but one that is well suited for that. Yeah, I mean, you could make up some measure, yeah, but it would be wise to use one that is proven and yeah, where you have some knowledge about its properties. Yeah, so we want to minimize the deviation between this hypothetical density Fy of y and the given density Fy tilde of y. Yeah? And there are several distance measures that we could use. So, and they both have their pros and cons, I would say. Yeah, so we use distance measures for quantifying the deviation between two random variables by means of their densities. In fact, you can compare random variables by many different means. I mean, we discussed that before. Yeah, we can use the cumulative distribution for the comparison, which makes sense. Yeah, but only in 1D. Yeah, after the, beyond 1D, it's not so simple anymore. You could use the moment generating function, whatever. Yeah, you can use different ways of comparing them. But especially when the random or when the densities or when the random variables have densities that are continuous, then you can use, for example, the Kullback-Leibler divergence. This is, yeah, I wrote that on purpose. This is not a distance. Yeah, it's a divergence. It is not a distance because we will see it's not symmetric. Yeah, and this KLD is given by in the following form. So we have a density ratio, F tilde over F, and we take the logarithm of this ratio. Yeah, perhaps you know log likelihood ratio tests and stuff like that. Yeah, that is very closely related. Yeah, so you take the two densities, take the ratio, the log of it, and then you multiply it by some weighting function, so that when this ratio does not behave nicely, when the density becomes smaller and smaller, one of the densities, yeah, so you weight it with one of the densities. Usually we take the reference density here, so F tilde. You could use the other one, but in that case optimization would be a bit unstable because you change your weighting function. So this is the usual way of doing it, but as this is non-symmetric, you could use the other way around also. Yeah? Would also be a Kullback-Leibler divergence. Yeah, and F tilde is our reference measure here because this is the given density that is not changed. We change this one. Yeah? So that would be Kullback-Leibler. And Kullback-Leibler is especially nice when you have exponential functions. Yeah? Because the log of an exponent always gives you the exponent, and everything will be much, much simpler. And there are some other advantages I will show you in a second. And then we have the perhaps more intuitive integral squared distance, where you take or where you subtract the densities from each other. Yeah, so F tilde minus F, square the difference, yeah, multiply by some weighting function that is optional, and then you integrate over everything. Yeah, this would be the integral squared distance. It's a distance, it's also symmetric, yeah, that is obvious, yeah, and you can show that it is a valid distance. Yeah. So we have these two possible ways of comparing the two densities, and let's begin with the Kullback-Leibler divergence. So what do? So we calculate the distance. This is the Kullback-Leibler divergence of F tilde of y and F of y. I plug them in. I can use the property of the log. So log of A divided by B is log A minus log B. So I can immediately use that times the reference density, F tilde. And now, as you can see, the only thing that we can influence is this Fy of y. This F tilde we cannot influence. So this is in fact a constant to us, yeah, and we can kind of split it off, and then we stick with this second part. So we have minus the integral over f tilde of y times the log of fy. Yeah? And when you look more closely, you can see this as an expected value. It's a nonlinear expected value. So this is the reference density, yeah, that provides the y values, and this is the nonlinear expectation, the log of f of y. Yeah? So you can see this as an expectation. And in fact, as we want to minimize d, you can see it as an expectation maximization, yeah, because we want to maximize this integral without the minus sign. We want to maximize this integral. Yeah. So find a function fy so that this is maximized. Yeah. Okay, let's do that. So what we have to do is we select some monotone increasing function t. Yeah, so y is t of x. Then when it's monotone, so it should be strictly monotone increasing. Yeah, when that is the case, we can find function r, the reverse function, yeah, that is directly related to this t. Yeah, because we have to convert between those two. Even if we find r and we want to sample from fy, we need to find the transformation t. Yeah, so they are closely related. So we have to find some function. Let's assume we have a function class where we select these functions from, yeah, and these are all monotonic and increasing. Then I can remove the absolute value here. And so we have fy of y is equal to fx, plugged in this r of y, this function, the monotonic function, times its derivative. When I take the log, I have to take the log. This is this hypothetical function that we plug in here, yeah, that we want to change to, it should be as close as possible to that f tilde. Yeah, then I have to take the log of it, and then the log of that is the log of this term plus the log of the derivative. Now that's nice about it. I can just decompose it into two additive terms. Yeah, so I have the log of the x density, yeah, but plugged in my reverse transformation plus the log of the derivative. So now what I can do is I can find a simple density here. And here you can see by what I mean as a simple density. So when you use the KLD, yeah, the Kullback-Leibler divergence. In that case, you should use a density that exploits the log in front of it. Yeah? So it would be unwise to use a sum of densities, for example. Yeah? I could say fx is like fx1 plus fx2. That would be crazy to do that, yeah, because then I wouldn't make sense of the log here. So what I should do is use an exponential density, just a simple term, yeah, and we can select a normal density, yeah, and perhaps I should write this down, what I did here, so that you can see that. So usually the normal density is 1 over 2 pi sigma squared, square root of it, and then exp minus 1/2 x squared over sigma squared. Yeah, and when I now select, so I want to get rid of everything besides the x squared. And I cannot get rid of the minus sign, of course. Yeah? So in that case, I select sigma squared is 1/2. Same here, yeah, and then I get this simple expression. Yeah. And why is it nice to just have the minus x squared? Because if I now take the log of it, this is just the log of the constant plus the log of the exponent of minus x squared, and this is just a constant minus x squared. And that makes it super nice to work with. Is that obvious? Yeah, just use the simplest function that you can find where you can sample from, and that gives a very simple expression when you take the log. Then I can plug this in here. So then I get, because I have to plug in r of y into this density fx here, then I get the constant minus r squared of y plus the log of r derivative of y. Yeah. So this is my final expression. And then what I can do now is I can plug this into the distance, into this distance measure, and it was minus integral fy of y times the log of fy, and that's exactly what I plug in here. And I pull the constant out again. Yeah, that is possible because that's constant times a function that should integrate to 1, so that is also a constant. Yeah, so I'm ending up with this expression. To be honest, this expression is perhaps not intuitive. Yeah, so it would not be intuitive to see why or how R should look like to minimize that. Yeah, that was probably a bit simpler in the ISD case, and we will come back to that again. Yeah, but still, if you minimize that, or alternatively, if you maximize this term here, yeah, then you find the mapping that maps the simple density fx into the complicated density fy tilde. Yeah. Do you have questions so far? Yeah.
So if the mean is not 0, we could just add a constant to the breakout end, right?
You mean the mean of what?
The mean of like reference, or
You mean we could use a mean on the reference?
I mean, if the mean of the reference is not 0, we could add a constant to it and shift it in the transformation, right?
Yeah, definitely, yeah. Yeah, here I just selected the simplest one, 0 mean and the right shape, yeah. It's not a standard normal, yeah, it has a variance of 1/2, so it's a bit narrower than the standard normal, but I think that's okay, yeah. As long as you keep that in mind during programming. We made this mistake, unfortunately. You have to take care of that in the end. Otherwise, it doesn't look good. Okay. Yeah, are there more questions? Yeah.
So like in what comes next, you first discretize and then probably optimize. So is it possible to do optimize like function analysis stuff, or that lead?
No. We will discuss that. We will discuss both variants. Yeah. Up to now, yeah, in Violet, up to here, you can use any function that is continuous, differentiable, yeah, and monotonic. Yeah, and from that, if you optimize within this function class, you find the right R for doing so. This function class is a bit too large for optimization, so you have to find a subclass, for example, radial basis functions or whatever, yeah, whatever comes to mind. So for example, you could use a radial basis function approach for R prime, and then integrate and make sure this is positive, and then do an integration and find R and plug that in here. Yeah? So you always have to make sure that you get a monotonous function, and one of the easiest ways is to find a positive function that you can guarantee to be positive for the derivative, and then take the integral to find the R function from its derivative. Yeah? And then you can use fairly large function classes, yeah, to do this optimization and find the right R. But we will start, after the break, we will start with the discretized case, because it's much easier to visualize. Yeah. Okay, so then we will do the break now, 5 minutes break. Okay, yeah, then let's continue. Yeah, we were just discussing how we can now do the optimization, by selecting an appropriate function class, perhaps a restricted one, and then doing the optimization of this function class and find the appropriate R function, the reverse function. Then, given the reverse transformation, we can find the forward transformation by inverting it, and then we can transport samples from the source density to the target density via this forward mapping. And to give you a little bit more insight, I decided to do it on a grid. And as we already had some examples for that, so we will use a regular grid, so we assume that we work on a regularly spaced grid. That is not directly necessary. We could, for example, take the derivatives also on an irregular grid, but it is much simpler, and as we need lots of grid points for a nice resolution anyway, it makes sense to have a regular grid. So what we do is, when we look at this integral that goes from -infinity to infinity, but over a density with a finite support usually. But still, if we want to discretize the entire domain, then we have to do something like that. So we have yk. So the discretized y domain would be k times h. H is the distance between two discretization points. And k would be element of z. So all integer numbers, also negative integers. But we will use a finite discretization in the relevant region. So we start with the discretization point y1, and then we equidistantly step to up to yn. So we have n discretization points, y1 to yn, and they have equidistance of h. Okay. Then we represent the reverse transformation R of y as values on the discretized y domain. That is shown here. So we have the y1, y2, y3, and so forth until yn of the y domain. This is the distance, h. Then we have the height of the function here at point 1. It's called r1. At point 2, it's called r2, and so forth. And then we do central differencing. So at every point, we look to the left and to the right, and we find the slope. In fact, in this case, we provide the slope directly. And this makes it symmetric. So usually you will see a forward or backward differencing schemes where the slope is between 2 points. The problem is we tried that in the beginning, and then it really gave us some asymmetries in the result. So it's much better to really define the slope on top of the considered point. So the slope is always defined in the middle here. It makes it a bit more difficult to calculate, but I think it's worth it. So we define R of yk, so the reverse mapping at point yk is called rk. The first value is r1. That we have to specify. It's kind of a global offset for everything. And from that on, we only define slopes. So we define one offset and then only slopes. And as I discussed for the more general function class a few minutes ago, then we calculate our function by integration. So we start with a function that can only be monotonic, because we start with positive increments. But I will explain it here. So we have these increments, and when you look closely, when you go from R1 to R2, you take half of the of this delta 1. Yeah, so delta 1 would be the difference between that point and that point. So we take exactly half of that because we go to the half point here, plus half of delta 2. Yeah? And the same for every following point. So it's always delta k plus 1 half plus delta k half that we add to the last map point. Yeah? And then we accumulate, it's kind of a discrete integration, and that guarantees that we get a monotonic function as long as these increments are positive. Yeah? The derivatives are obvious, are these delta k's divided by h, but you can also motivate it by calculating central finite differences. So r prime, the derivative at yk, we also call that rk prime, yeah, is approximately the underlying continuous function, let's say, yeah, if there were one, at yk plus h over 2, so half the interval, yeah, minus r of yk minus half interval, yeah, divided, yeah, it's a finite difference, so difference quotient, yeah, so we approximate the derivative by taking the distance in the y direction divided by the distance in the x, yeah, this is then the y direction, yeah, but you know what I mean, yeah, along the abscissa, yeah, here, yeah, and divided by h, yeah. And this gives us directly delta k divided by h, and for all n, yeah, k is equal to 1 up to n, yeah. Okay, so, and when I now guarantee that the increments are positive, yeah, so that we only have positive slopes, then the function that I accumulate here, this discrete function that I accumulate, is monotonic. Yeah. Or strictly monotonic if they are really positive, or monotonic if they are non-negative, these increments. Then what I can do is I can find a simplified expression for this d. So d was a constant, perhaps we can go back. Yeah, was this constant times the function of the then integral of the function, then minus r squared of y plus the log of r prime. Yeah, this was our function, and here we have this approximation of the derivative on our discrete domain, and here we just have to plug in the domain points, yeah, for this y, the discretized points of the domain. And if we do that, we get a sum, yeah, times h, yeah, the increment, the distance between two quantization values in the y domain, and then the function, the density, evaluated at the discretization points, then the map points at point k, and then we have the derivative is just delta k over h and the log of it. Yeah? That's it, and we sum over it, so very simple. In fact, when you recall what we did for Monte Carlo integration, you could also write this or rewrite this as an integration over a uniform density. Yeah? That's why we get this h times this, yeah, and the sum instead of the integral. Yeah. We could do importance sampling and stuff like that, but here this is just an equidistant quantization. Yeah. And no weighting with the density in it. So the density is just evaluated, yeah, at equidistant points, and we just get the density values at these points. That's it. Yeah. Okay, then, when we now perform the actual optimization, we use the parameter vector provided by the optimizer, and then convert it to the required values of rk and delta k. So, in our case here, the parameter vector that we get from the optimizer is called ADA vector, and it's from r to the power of n plus 1. Why? We have the increments plus we have the offset. Yeah, so the offset is an additional value that shifts, in fact, the entire mapping. Yeah, so we have this offset plus the increments that gives us the mapping. So when we extract the values from the parameter vector, then R1, this offset, is the first value. That's how we allocated it. So it's eta 1. And then we extract the increments, delta vector, is P of eta from, and this is the standard notation for this, from 2 to n plus 1. Yeah? So we extract the remaining values from the parameter vector. But now, in order to use an unconstrained optimizer for that, yeah, we have to make sure that our accumulation routine just gets positive values. And so we use a function for that, yeah, thanks to my colleague that is sitting here, yeah, who defined this function in a recent paper. We call it P of x, or positive pos of x, yeah. So this is a function that uses an input x and outputs a positive value. It's just a function like that, yeah. It's like this ReLU function we saw, just a little bit smeared out, yeah, and it maps all values from minus infinity to infinity to just positive values, yeah, or non-negative values, yeah. Okay, yeah, and given this function, we then use these deltas to accumulate based on R1. So we use R1 and then we add continuously onto it, yeah, by just averaging subsequent increments. Yeah, and that's how we build up this monotonic function, yeah, over the discrete domain. Yeah. To show it again, yeah, then we get this monotonic function. Yeah. And the optimizer now kind of, yeah, in that case we use automatic differentiation. Yeah, the optimizer differentiates this distance measure and then finds the values for R1 and all the deltas until we have a nice fit. Of course, you need an initial value, an initial guess for doing the optimization. Yeah, if that guess is way off, you wouldn't find the optimum. But we found that this was quite robust. Yeah, and I will show you some examples or some results in a second. Yeah, what you can do is a similar procedure for the integral squared distance instead of the KLD, the Kullback-Leibler distance. Yeah, and if you remember, this was just f tilde of y minus fx plugged in the reverse mapping times r prime, yeah, of y, and then we take the difference and square it. Here I use no weighting function, but we could, and then we integrate, and this integral is then approximated as before. We use the sum. H is the increment between the quantization intervals, the quantization interval, in fact, and then we just use this difference again. Yeah? And the derivative is again just the increment divided by h. You know? And we can also optimize that. You know? Yeah. What we obtain, as I showed you up to now, is when we perform this optimization, we obtain always the reverse transformation. It's a very elegant way of doing it. Yeah? You just plug in the reverse transformation everywhere and do your calculation, yeah? And we get this result. Yeah? And I think that's easy to do and very elegant. But it also has some disadvantages, and we will discuss them in a second. Yeah? But what we get is, when we have the reverse transformation, we can now explicitly write down an approximate representation of this desired density fy tilde of y. That's here. So we now get an approximation, yeah, depending on how fine we do the discretization. Yeah, and we can write it down explicitly. Yeah, and yeah, and now we can kind of evaluate this desired function by plugging in values here, for example. Yeah, so you can evaluate values of your desired function. Yeah, or you can sample from it. But when you want to sample from it, yeah, when we want to transform samples of the given density fx of x, then we need the forward mapping. Yeah, that's important to keep in mind. Yeah. So if we do not only want to write down the density, but if we want to obtain samples from it by sampling from the simple density, then we require the forward transformation. Yeah, y is t of x, and that's r to the minus 1 of x. So we have to do the inversion. Yeah, here in the discrete case, in the strictly monotonic discrete case, it's very simple to do this inversion. Yeah, you just step along the points and just invert your mapping. Yeah, by switching the roles of x and y. That's simple to do. In general, that's usually not so simple to do. When you remember this, for example, RBF function that I mentioned in the beginning as a function representation, yeah, and we want to invert that, then you would have to do it numerically and fit, for example, another RBF function to it, stuff like that. Yeah, so that's not so simple. So that's why we decided in the end to show this to you in a with a discrete mapping or with a quantized mapping, because then everything is so simple. But what we could do is, instead of using this optimization approach, yeah, we could use the reverse optimization. Yeah? So up to now, we performed the optimization via the comparison of the densities. We performed that in the y domain. Yeah? So as you see here, everything is done in the y domain. So in the domain where we want to map to. Yeah? That also has some problems. Yeah? For example, even here with the simple discretization, we have to discretize the y domain that we, in fact, don't know. Yeah? So we are given this density in the y domain, but we don't know where this ends. So when you are given even an analytic expression of a density, yeah, a complicated density, you have to tell me where the support of this density is. This is very difficult, yeah, to do. Yeah, so even if you have a Gaussian density and you plug in some polynomial in the exponent, yeah, and then you plot it, yeah, you will see this can have some unexpected form, and you don't know where it ends. So if you do the discretization that I showed you, you have to know the discretization domain. Yeah? So in the 1D case, that can be done by trial and error and stuff like that. Yeah? So that might be okay. But in general, you have to be careful. You are working in the domain where you map to. And this is a density that you don't know as well as the density that you have in X, yeah? Because you have full control over that density. You know, in our case, fx was even a Gaussian density, so very simple to handle. Then fy of y can be a very complex density, so discretization is not trivial, because, for example, we need adaptive discretization, or we need samples from it. You know, that might be very difficult. Yeah? So it's not always wise to do it in the y domain, and we only get r of y, yeah, so the function r of y, we do not get t directly. So what we could do alternatively would be, we use the dual relation, yeah? And even outside of discretization, yeah? So when you use continuous mappings, you always have these two options. Yeah? You could use the dual relation between the source density fx and the target density fy. Fx of x is equal to fy of t of x times t prime of x. That is what we can also use. Yeah? So, in fact, as you see here, we have, in fact, 4 dualities. Yeah? So 2 in each direction. Yeah? So this is just the reverse direction. Now, I in fact map from Fy to Fx, which is not a problem, as you can see. These mappings are all reversible. And, but what we can do now is we can now define a distance of the x domain, which might be much, much simpler. Yeah. So this is the source domain that we use here. So we have this distance measure, and now we compare it over the x densities. So this would be the given density, with a tilde. This would be the hypothetical source density, And for example, for the ISD, that now would be the integral over f tilde of x minus, and now the hypothetical density plugged in, Fy of t of x times t prime of x, square the difference times the weighting function, and then we integrate. So this would be an integration in the other domain. This is not guaranteed to give you exactly the same result. Of course not, because it depends on the distance measure, and it depends, of course, on what densities you compare, because these densities are transformed between the domains. That does not give you exactly the same t as you would get from optimizing the r in the other domain and inverting it. It's a different one. I think it will usually be very close to it. Then we use a similar discretization scheme for the x-axis, define a similar discrete forward transformation, t of x, also by integrating over the increments. And then after the optimization, we have an approximation of the source density now. So of fx tilde, this is what we provide. And that can be exactly the same that we had, before, because it was so convenient. And now we get a distance measure between these two, and of course then an approximation of this density given in this standard form, but in this dual form to the one that we used before. Are there questions concerning that? Yeah.
In the optimization step, you provided the function to make the values positive. So my question is, why isn't you used like this barrier methods in optimization to basically put the constraint into it?
Yeah, definitely. You can just use an optimizer and tell him, I just want to use positive values. No problem.
Okay, but you got better results with this?
I usually do it this way, So when I can avoid constraint optimization, I do it, But you're right, you can use penalty functions, barrier functions, But this transformation is nice. You can use all the unconstrained techniques that you have, And we recently did that for Kalman filtering, where you can use a Kalman filter for just a regular domain and use it for problems that should be positive. So that's why we did that. And that gives nice results. And in fact, I would like to show you some results. Just a second. Yep. Okay. So this is now a live document that you will also find in Ilias, so you can just open it. And here we use the Kullback-Leibler divergence and finite differences for learning a mapping. So for learning kind of an implicit function representation. And just as a summary, this is the given simple function, this fx of x. This is the complicated function, and we see two. The given one, f tilde of y, and the calculated one, fy without a tilde. It's shown here, This is the given one, and this is the calculated one, but they are more or less exactly the same, So you cannot see the difference. This is the initial mapping that we give the optimizer, just more or less a random mapping. And this is the mapping that the optimizer calculates. and then it maps this function to that. So this is in fact the reverse mapping, so it would map this function to that function. Yeah. But as we saw, yeah, I need this for the optimization. This is how it is done. Yeah. So just some explanation so that you can understand it if you look into it. So we set up the grid. Yeah. So these are the y values for the grid. They here go from -6 to 6. H is selected as 0.1. That's the interval width. Yeah. Then we have Cx is 1/2, and this is our standard density. It's not a standard normal density in terms of unit variance, but this density where you just have e to the minus x squared. Yeah. Then we can have a Gaussian density that we provide for approximation, or some complicated variance shifted Gaussians, then a Gaussian times a sine function, then a very fancy density where you have an exponent of a polynomial, which is in fact first unnormalized, but for the ISD it will be normalized. For the KDL it does not have to be normalized. Yeah. So this function, it is just for plotting purposes that it has been normalized, but for the comparison inside the distance measure, no normalization is required, because that gets lost in the logarithm part, which is nice. Yeah. So the normalization constant is just another constant that we can forget about in the optimization. Yeah, because it's multiplicative in the density, so we can forget about it. That's very nice about the KLD. Yeah. Then we set up an integration problem to get, for plotting purposes, as I said, the normalization constant. Yeah. Then we have this positivity function. Yeah. That does. Yeah. Here is also written down. It's an alternative to the constraint that you mentioned. Yeah. You could also use constraint optimization. We use this mapping function. This is the function that converts the parameter values of the optimizer to the mapping. Yeah. And here you see the extraction. Yeah. So we extract the first value as the offset, and then we accumulate over the average of the increments. Yeah, that is done here. Then we have the objective function for the KLD, that we wrote down. I hope I can zoom in. Yep. Yeah. This is the KLD objective function, including the minus sign. Yeah. So that we minimize instead of maximize. Then we have the objective function itself, where we convert the values of the optimizer, calculate the desired values, offset, increments, everything, and then we add up all the distance values, from 1 to n over all the quantization intervals. Then we take some initial guess. This is the initial offset as -2, just to have some offset, and then we have some random values for the mapping. And then we set up an optimization problem with an automatic differentiation, and then we do some iterations with this Broyden, Fletcher, Goldfarb, and Shannon, BFGS algorithm. It's a quasi-Newton method that we usually use, and that just does a downhill search, and finds the minimum. And then we just do some plotting, and this is the result. And I can, I think I can change some things. And then I can run it again. Okay.
Was ja nur den Wert verändert.
Mm-hmm. Perhaps we can try some plausible value. Oh, okay, now it worked. Perhaps you can change this parameter. Mm-hmm. Mm-hmm. Okay, yeah, and you see it's a bit of a different function, yeah, here it's a bit different, and it finds the mapping again, yeah, and from here to here. Yeah, and now you could sample from this complex density. Just take some samples from the normal distribution, map them over the inverse mapping of this, yeah, this is R, so we need T, yeah, just map them and you would get samples of this crazy looking density. And I think that is something, yeah, and for 1D, that would be practical. Yeah, so you could use that. If you need some samples, yeah, you could just simply use that routine and get some samples. And you could use, if it would be too complicated, and here you can see that it would be difficult to guess the domain of this function. Yeah, but we know the domain of this function here. That is simple because this is just a narrow Gaussian. Yeah, so you could alternatively do the optimization in this domain, directly get your T mapping, what I explained before, yeah, and then you would also get samples from this, yeah, perhaps even as a simpler alternative. But I think that makes sense as a procedure, and even with the discretization in 1D or 2D, and it's simple to understand. Then we did a similar thing with the ISD. So the setup, I don't have to explain that to you now, yeah, is very simple. Instead of this complex positivity function, we now use x squared. That seemed to work a bit better here in that case, but otherwise we just changed the objective function. So this is the ISD, so exactly as I showed you, yeah. So this is the given function, fy, evaluated at the y points, minus fx evaluated at the mapping at this point k, and then just the approximated derivative via central differences, yeah, and this is then added up and optimized and gives you, for example, here this result for this density, yeah. And you can play around with this a bit, yeah. You can just select different densities. We also have some examples here that you can just uncomment and then, for example, this times a sine function. In fact, I can try to run this. I have some minutes times 10. So what do I have to comment out?
If y below, so 5 lines below.
And then
Shift and
yeah. And this looks also nice, yeah, as you can see. So this is now a Gaussian times a sine function, yeah, and it maps from this blue function to here, and here you see this strange mapping function, yeah. It looks a bit crazy. This is the initial guess that we provided, and this is then optimized to get this mapping function. And you see how this mapping, yeah, is especially has a strong slope, yeah, when we have high density values here and stuff like that, yeah. So I think it gives a nice visualization. Okay, are there questions? Yeah.
So this method would not work as well for higher dimensions, is that right?
This would work for like 2 or 3 dimensions, but even in 2 dimensions, it is much more difficult to implement, yeah. But it would work for low-dimensional cases. But if you, let's say, have 10 dimensions, that would explode in terms of grid points. Yeah, so using a grid in higher dimensions, let's say then 4, 5, 6, depends, yeah, is not wise usually, but could be used, yeah. But I mean, the main issue here with this was that we used that for visualization purposes for the lecture. Yeah? For the one-dimensional case, I would say it is usable. Yeah, you can use that in a practical setting. Even it's quick, everything. Yeah, but even for 2D, it becomes complicated. Yeah, also for setting it up. Yeah.
I just was wondering, compared to Markov-chain Monte Carlo sampling, like of course in higher dimensions, probably MCMC is far better because I don't have to constrain it to do the optimization. But for like a one-dimensional case, would this be faster or better even than MCMC?
Yeah, the advantage is once you have it, once you have the mapping, from then on it's free. Yeah, so setting up the mapping, but here we have a very fine resolution. I played around with, let's say, 0.5 instead of 0.1, and it also worked okay. Yeah, or let's say 0.25 or so. So you can be a little bit more rough, and it still works. So it would be quick to set up the mapping, and from then on it's free. And Markov-chain Monte Carlo always has to recompute things. Yeah, but it's a different problem setting. This is constructive. That's the label of this part of the lecture is constructive sampling. Yeah, but Markov-chain Monte Carlo does not need to construct something. Yeah, it just samples from a given density. Yeah, that's the difference. Mm-hmm. It's much more versatile in that regard. Yeah, but computationally complex. Mm-hmm. Yeah.
Maybe you already mentioned it, but has it worked on other limitations on the target function, or can we replicate that to any one-dimensional target function?
Yeah, I would say besides pathological functions, there might be some, with very high slopes, discontinuous, whatever. Yeah, but let's say we have a continuous density. In that case, we do not even need for the IST. We need it, at least for this program. But for the KLD, we do not even need the normalization constant, and we can just do the optimization for any of these functions. There are no requirements. I'm not sure about, to be honest, about. Even discontinuous functions should work. So discontinuous densities should even work. We never tried. It's not a problem, right? Yeah. So should even work for discontinuous densities. So I think that's very versatile in 1D, at least. Mm-hmm. Are there more questions? Okay, I think then that was everything I wanted to show you. Then thank you very much. And now we have 2 weeks off. Yeah, and then see you in 3 weeks. Yeah. Okay. Bye.